Welcome everyone to the grand finale of our Machine Learning Explainer series. Now, if you've been with us from the beginning, you've already learned the absolute fundamentals of how machines learn from data. But today we are stepping into the big leagues. We're going to demystify the ultimate predictive algorithm, the exact one that dominates data science competitions worldwide and powers some of the most advanced systems at top tech companies. We are talking about gradient boosting. So think about this for a second. What if every mistake you made could literally be corrected by the next version of yourself? Imagine you're a student preparing for a massive final exam. You take a practice test and, you get a few questions wrong. Now, instead of just studying everything all over again from scratch, you create a clone of yourself, like a little mini helper, whose sole purpose in life is to study only those specific questions you got wrong. Then you take the test together. You still miss a couple of really hard questions, so you create another clone to focus exclusively on those new mistakes. If you repeat this hundreds of times, learning exclusively from your wrong answers, eventually you become nearly perfect. Well, that is the absolute genius of gradient boosting.
Here's our roadmap for this explainer. We're looking at 1. The power of mistakes. 2. How gradient boosting works. 3. Looking under the hood. 4. Strengths and weaknesses. And 5. Real-world machine learning. Okay, Section 1. The power of mistakes. Let's redefine some of this intimidating machine learning terminology into friendly, relatable concepts. Here's the formal definition. Gradient boosting is an algorithm that builds models sequentially, where each new weak learner corrects the errors of the previous one. Let's break down those two keywords. First, boosting. This simply means taking a bunch of weak learners, usually very small, simple decision trees, and combining them to make one incredibly strong learner. And gradient, that really just refers to the math under the hood. It means the algorithm uses optimization to take the steepest path down a curve to minimize our loss. Or, in simple terms, to reduce our errors as fast as possible.
Moving right along to Section 2, how gradient boosting works. The mechanics here are actually just a highly logical sequence of corrections. Step 1, make an initial prediction. This is usually just a very basic baseline guess, kind of like taking the average of all the numbers you're trying to predict. Step 2, calculate the residuals. Now, a residual is really just a fancy word for your error. It's the exact difference between your baseline guess and the actual true answer. Step 3, train a new weak learner. But here is the secret sauce. This new little decision tree is trained to predict the errors, not the original target. It focuses entirely on fixing what the first guess got wrong. Step 4, add the new model's predictions to the existing ones. And finally, Step 5, repeat. Over and over again, continually chipping away at the remaining errors until your combined model is highly accurate. All right, Section 3, looking under the hood. Let's see how all this builds into the actual equations. If you look up gradient boosting in a textbook, you're going to see a massive, terrifying formula with sigmas and gammas, but we can distill all of that down. The formula for your final model simply comes down to your old guess plus your learning rate multiplied by your new correction. That is literally it. Every time the algorithm cycles through those steps we just talked about, it takes what it already knows, calculates a small correction, scales it down a bit with the learning rate so it doesn't overcorrect, and adds it to the pile. The entire goal here is just to minimize the loss function, which is really just a mathematical way of saying make the errors as close to zero as possible. Now think of these hyperparameters, things like n_estimators, learning rate, max depth, subsample, loss, and min samples underscore split, as levers you pull to tune your machine. Imagine you're a DJ at a mixing board. n_estimators, for example, is how many trees or mini helpers you want to build. More trees can mean better accuracy, but it takes longer to train. The learning rate controls how big of a step each tree takes. Max depth controls how big each individual tree is allowed to grow. And we actually keep this small so our helpers remain weak learners and don't just memorize the training data. It is incredibly satisfying to play with these levers and actually watch your model's accuracy climb. And here is the proof that you can do this yourself right now. Achieving this mathematical magic only takes a few short lines of Python code using the standard scikit-learn library. You initialize the classifier, set those hyperparameters we just discussed, hit fit on your training data, and predict on your testing data. It's beautifully accessible. You absolutely do not need a PhD to start building world-class predictive models today. Section 4, Strengths and Weaknesses. It's time for a quick rapid-fire reality check because, no algorithm in the world is completely perfect for every single scenario. Let's weigh the scales. On the advantages side, gradient boosting consistently achieves the absolute highest predictive performance on structured, tabular data. It naturally understands complex, nonlinear relationships, and it even handles missing data gracefully. It's a total powerhouse. But on the flip side, remember those DJ levers we talked about? Well, the algorithm is highly sensitive to them. If you tune them poorly, your model will suffer, and it's definitely prone to overfitting. Also, because each tree relies on the mistakes of the previous one, you have to build them sequentially. You can't just build them all at the exact same time, which means training can be significantly slower. Section 5. Real-world machine learning. Let's ground all this theory into reality to show exactly why banks, hospitals, and tech giants rely on this process every single day. Gradient boosting isn't just an academic exercise, it's out there protecting you right now. When an email provider successfully filters a really clever phishing scam out of your inbox, it's often gradient boosting at work. When a bank evaluates the risk of a loan or spots a fraudulent credit card swipe in real time, they're relying on the exact sequential learning we just talked about. From e-commerce predicting sales trends to healthcare assessing medical risks, wherever structured data exists, gradient boosting absolutely dominates.
And when professionals actually deploy these models in the real world, they usually turn to some heavy hitters. Beyond the standard scikit-learn library, you'll frequently hear about XGBoost, which stands for Extreme Gradient Boosting. It is heavily regularized and extremely fast, basically making it the undisputed king of data science competitions. Then there's Microsoft's LightGBM, designed to be blazingly fast on massive data sets, and CatBoost, which handles categorical features automatically. Knowing these names gives you the vocabulary of a true machine learning practitioner.
The journey does not end here. It begins here. By understanding gradient boosting, you've really reached the pinnacle of traditional machine learning. By understanding how to learn from mistakes sequentially, combining hundreds of simple helpers into one powerful model, you can achieve accuracy that was once thought completely impossible without deep neural networks. You now possess the foundational knowledge of a machine learning engineer. But the true test of everything you've learned isn't just in understanding the theory, it's an application. The next step is to get your hands dirty. Go find a real data set that interests you, load it up, pull those hyperparameter levers, and watch as your model learns from its mistakes, getting smarter with every single iteration. You have the tools, you have the knowledge, and you have the power to predict the future from data. So, what will you build first?